So I'm being stared down. So, welcome to today's class. Today we are gonna finish chapter 3, where we had been talking about forces. And basically, most today I'm not gonna talk about forces, although I'm gonna talk about one last one for the first 3 slides, but effects from forces. So, um, let's talk about one more special force, and that is the buoyant force. Anytime something is surrounded by a liquid or a gas, it feels what is called the buoyant force, which was first worked out with something called Archimedes' principle. Archimedes' principle states that if an object is completely or partially submerged in a fluid, it is buoyed up by a force whose magnitude is directly proportional to the volume of displaced water. What that means is I have right here a can of water, and the water is filled, you can't see it because it's not see-through, it's filled up right to the spout. If I go and put like a hunk of aluminum in it, some water flows out. That water that flows out, that is the displaced water. That if I go take some water and my water level, I meant to grab my marker, my water level is basically right at my hand. If I put something in it, the water level goes up higher because it displaces some. And what happens when I threw this Yoshi in here, because it's a Yoshi I threw in there, is that it's going to displace some of the water. There is a force acting on Yoshi, pushing him up. And that force is the weight of the water displaced. That is called the buoyant force. Anytime anything is submerged in a fluid or a gas, it feels a force upwards. Now, how big that force is just going to be set by the volume. But whether or not something floats or sinks, well, that's going to be a little more complicated. If you go and drop something into, and let's just deal with liquids for now. I'll come back to gases in a second. The net force, the sum of the forces, will be based off the density of the object and the density of the fluid. Because when I drop this Yoshi in this water, gravity pulls him downwards. The buoyant force pushes him up. He sinks because the net force is down. The force of gravity is bigger than the force of the buoyant force. And what you'll have is because the force of gravity is just being mg, and the force of the buoyant force is the weight of water, so the mass of the water times g, it actually comes out that it's only density that matters. An object will float in a fluid if the density of the object is less than the density of the fluid. This little styrofoam ball is less dense than water, so it floats on top. If I fully submerge it, it'll float to the top. That is because it is less dense than water. Any object that is more dense than the fluid will sink. That's why Yoshi sank to the bottom. He is more dense than water. And in general, if something has the same density as the fluid, it'll sit at the same spot. This GIF to the right is, I think it's honey, water, and oil, just the water has food coloring. But it's a more dense liquid, a middle density liquid, the least dense liquid. And what you'll find is when they drop different things in, they sink to different spots. The metal is more dense than everything. The grape here is somewhere density between this orange liquid and the blue liquid. This cap's density is between the blue liquid and the yellow's liquid. And so it's whether or not it sinks or floats is just based off these densities. Anytime you're working if something's going to sink or float, you don't care how much it weighs, you care about the density. This is why an aircraft carrier sinks, aircraft carrier floats, I misspoke, while a bowling ball sinks. A bowling ball is a lot lighter than an aircraft carrier, but it is less dense. Wow, I am failing miserably today. A bowling ball is more dense. A bowling ball sinks because it's more dense than the aircraft carrier, density being mass over volume. This GIF to the right is someone making lead float. This lead floats because it's being dropped into mercury. Mercury is more dense than lead, so lead floats in it. Any questions though?
Nope.
Okay, so that's it for forces. The rest of this chapter is going to be how we use forces. And the first thing I'm going to talk about is torque. Okay, If you want to make something accelerate in a straight line, you apply a force. If I want to make myself accelerate, I'll apply a force, I'll accelerate. F equals ma, there we go. But anytime if you want to, instead of making something move in a straight line, if you want to make something spin, you apply a torque instead. Torque uses the Greek symbol tau. Looks like a weird little T, and its units are Newton per meter. If I want to spin this, there we go. I'm going to push on it to cause the spin. I'm not going to say I'm applying a force. I'm going to apply a torque, pushing here, giving it spinning. This also works anytime you want to like open a door, anything on a hinge, you apply torques. Once again, symbol is tau, units is Newton meter. And torque is just defined as how hard it is to rotate something around an axis. The equation for torque, this is a simplified version, but if R and F are perpendicular, as long as your force is perpendicular to where you're going, the magnitude of torque is RF. Is going to be how far away you applied the force to the pivot point and how hard the force is. I'll have a little bit more pop up and then I'll talk about. And so if I want to make this thing spin, I apply a torque. What I'll say is I'll apply a force somewhere along it. That would be F, and I'll say how far away from the pivot point, in this case the pivot point being the middle because that's what it pivots around, how far away from that pivot point did I apply the force? If I apply it really close, that'll be a small torque because R is small. If I apply it way out here, it'll be a large torque because R is big. Note, this assumes R and F are perpendicular. If I pull this straight to my right, I don't know what direction is to you guys, probably left. If I pull this straight to my right, it's not going to spin. It's only when I push it down or push it up. This assumes R and F are 90 degrees from each other. Now torque is pretty useful in a lot of various things. I will start by saying is if you ever want, sorry, the cat is now batting at that. If you ever want to turn like a bolt and you can't turn it, more torque is almost always the answer. I have here a bolt that I tightened the hell on with a tiny little wrench. If I take this wrench and try to push it, I tightened it super hard so I can't actually loosen it. If I take this same wrench and put a big ass lead pipe over the end and push it way out here, I can turn it with ease. Well, I think I just knocked it off and didn't actually turn anything.
So is this kind of like letting the tool?
Sorry, is this kind of like what? I misheard that.
I know it has to do with the science part with like a axe per se. If you hold it at the top and try to chop wood rather than holding it at the bottom and letting it fully go through.
Yeah, that is actually part of it. It is with the torques because it's where you're applying the force. When you
Like,
apply the force a further distance away, because
Yeah.
with an axe, okay, this is gonna be my tiny axe. You're pivoting it around you. I'm gonna do it with my elbow, but really it's probably a lot more body swing than just elbow, but I'm doing my elbow to make life easy. If I pivot around the elbow, the force it's gonna apply is how long to the edge of the axe to that point. If I'm just going eek instead, it's gonna be a lot less torque than if I'm going like this. So that is exactly why.
Maybe.
And so yeah, you got something you can't turn or something like the wood chopping, get a longer piece. If you increase the radius of turning, you'll apply more torque. You got a bolt you can't do, get a bigger wrench. If you have a big enough wrench, you'll always be able to turn it. Okay. Okay, I'm gonna jump topics entirely. I kind of the one thing I hate about this class is that because it's like a low level of not low level, that's a bad way to say it, because it's like introductory version of everything, it kind of just jumps on each topic for a second, so there's like horrible no segues. So next topic. The other thing I need to talk about with this chapter is the idea of momentum. Anytime if you want to stop something that's moving, or if you want to make something that isn't moving move, or you just have a collision. If I take two objects and say, hey, look, these two things bounce off each other like so. You're going to have to deal with the idea of momentum. Momentum is dealing with the fact that mass or inertia, whichever one you want to call it, wants to resist changes. And momentum is how much you need to overcome the inertia. Because it's not good enough to say, okay, I need to do an acceleration, but how hard is it going to be? Momentum, which uses the symbol P. I don't know why momentum uses P. It does. I apologize. But momentum, or at least linear momentum, which uses symbol P, is mass times velocity, and has units of kilogram meters per second. Momentum is a vector. It matters what direction the momentum is. It'll always be the same direction as the velocity. And I mean, this is the difference of, someone throws a baseball at you and you catching it versus someone throwing a bus at you and you catching it. That's what momentum is. It is the mass times the velocity, and will be how hard it will be to stop an object. Sorry, there's a weird typo here that I'm fixing. And extra spaces here. Okay? Now, if you have a collision, like these two guys I was showing here, anytime you have a collision,
I used those in high school, those little carts. I took physics. I didn't get a high enough grade. I wouldn't do it. But
if we were in person, we'd be playing with them, but sadly, online. Anytime you have a collision, the net force, and assuming the net force on the system is 0, what that means is, going back to these cars real fast. If when these were coming into bouncing, if someone ran in from the side and just flipped the whole table, that would throw it off. This GIF I have here, if a third person came in and just decked somebody as they were running forward, that'll throw it off. But assuming no external things happen, assuming no one shows up out of nowhere and messes with the system, in any collision, the initial total momentum is the same as the final total momentum. Momentum is mv. And anytime you have two objects colliding, what you'll say is the initial momentum of one thing plus the initial momentum of the second thing is the final momentum of one thing plus the final momentum of the final thing. In this, what looks like deadly collision here, what we'll say is we have a guy and a girl running in. They both have momentum. And so the initial momentum of the system is his momentum plus her momentum. After they collide, they both have momentum. And so the final momentum of the system is his momentum plus her momentum. And the total of the initial equals the total of the final. Now, I will say you've got to be really careful in negative signs here. I would say that she's moving to the left. Therefore, her initial momentum is negative because it's to the left. Once again, just like earlier, we're going to do everything to the left as negative, everything to the right as positive. And that when I take these cars and bounce them, let's actually have a different one, I'll just say the initial momentum equals the final momentum. And I can say for the blue car, the mass times the initial velocity of the blue car plus the mass times the initial velocity of the red car, once again, the red car would have a negative velocity, will equal, okay, why are you here? The mass times velocity of the blue car, which is now negative, plus the mass times velocity of the red car, which is now positive. Make sense? Any questions? I'm going to do an example problem that's a little harder than something I put on the exams or homework, but I just get this idea across. And then I'll do one more along the lines of the level I expect you to do. And this one says, Magneto floats towards the X-Men at 2 meters per second. Someone throws Wolverine, claws first, at Magneto, a move known in the comics as the Fastball Special, at 15 meters per second, directly at Magneto. Magneto, seeing a metal skeleton mutant flying at him, uses powers over metal to repel Wolverine directly backwards at 8 meters per second. Upon repelling Wolverine, what is Magneto's new velocity, magnitude, and direction? See, that's basically the same as this. I got things coming in, and they bounce off. And I say, given the mass of both of them, Wolverine's mass and Magneto's mass, how fast and what direction does Magneto move? So I'm going to shrink this a little bit to make space. And I'll say, I know Magneto is initially moving at 2 meters per second. Wolverine is initially moving at 15 meters per second. But if I look at my picture, it's to the left. And since it's to the left, I'm going to say Wolverine moves at negative 15 meters per second. And that's my initials. They're both coming in. After the collision, after they bounce, I'll say Wolverine is now moving at 8 meters per second. And it's positive again. It's positive again because it's to the right. And I give them masses. The mass of Wolverine, the mass of Magneto. And I say, what's the velocity of Magneto final? And so what I'll do is I'll just say initial momentum equals final momentum. Momentum is mv. And I'll just view each thing as a piece. Initially, I got Magneto and Wolverine. So my initial momentum is the initial momentum of Magneto plus the initial momentum of Wolverine. Final, I have Magneto and Wolverine. So my final momentum is the final momentum of Magneto plus the final momentum of Wolverine. And what I said here is, hey, what is the final velocity of Magneto? And I can just solve for this term. What I'll do is I'll subtract this piece right here from both sides and divide both sides by Magneto's mass. And this will tell me exactly how fast he's moving. Just by plugging in some numbers and getting an answer. Now it's of note I get a negative answer. And in fact, I get a huge negative answer. But that's okay. The negative just means he's moving to the left. That if he pushes Wolverine off him, he's going to push himself back. And quickly, because Wolverine is heavy as balls. Any questions? Let's simplify it and do the type of thing I expect you guys to do. Earlier in this chapter, I talked about with Newton's third law, that if you fire a gun, there'd be recoil. That's Newton's third law. We can use conservation of momentum to work out exactly how much. Because, let's go back to my videos. This is the recoil problem right here. These two things are stuck together, and when I hit the spring thing, they push each other apart. What I can say is this is the same as a collision. This is a conservation of momentum problem. Initially, nothing is moving. Since they're stationary, they have zero momentum. And so my initial momentum is zero. After I hit it, they're both moving. They're both moving, so they both have momentum. But initial momentum must equal the final momentum. And so what that says in this collision is that my final momentum must also be zero. And even if I make them so they don't weigh the same, like this one, the red car weighs a lot less than the blue car, that will still be true for any combination. And what we'll say is this conservation of momentum. For this recoil problem, initially, everything is at rest. Nothing is moving. And that means my initial momentum, which I'm going to use, I'm going to do this as if it's a cannon, the cannonball. Sub C will stand for cannon. Sub B will stand for cannon, will stand for ball, because I didn't want to use cannonball because I didn't want to use C twice. So C is cannon, B is ball. I'll say initially, I have the momentum of the cannon plus the momentum of the cannonball. But neither one's moving. And so the momentum is zero. But if a cannon launches a cannonball, what's going to happen is after it fires, they'll have momentum. The cannonball, or in this case, the coats, if I do it with this guy, is going to go flying in one direction, while the cannon, or the blue coat, goes in the other. And so my final momentum will be the momentum of the cannon final plus the momentum of the ball final. But since P initial equals P final, we can use that to say that MCVC final plus MBVB final, my final momentum, must be zero. What I would do is I would subtract this MBVB final from both sides and divide both sides by the mass of the cannon. And I get this equation. This is the recoil equation. Anytime you're at rest and you launch something, you will get a velocity from it. Now, if you're like going back to the gun idea, if you brace, you can keep it yourself from flying backwards, mostly because friction and other forces opposing it. But without friction, for any time you launch something, it will push back. And it's gonna happen no matter what. If you make out a real big cannon, it's gonna have a real big recoil. And you can't do away with it. It's going to happen. And so you need to prepare and brace for it. If you like, this guy flies back a ton, but is made to account for it. If you don't account for it, it'll just break itself with time. And anytime you launch anything, the velocity that you'll go will be negative because it'll be the opposite direction. The mass of the ball, velocity of the ball over the mass of the cannon. And what I'm going to do is say B here, which goes, that's going to be whatever is being launched. And C is whatever is doing the launching. And we can just use this equation to talk about the velocity of anything in the recoil problem. Where if I'm launching something else, like Luigi throwing a Koopa shell in Mario Kart, I can say that instead of a cannonball and a cannon, I got a shell and a Luigi. And I can use them accordingly. So let me do the problem. This is an old exam problem. And what it says is Luigi is sitting stationary in a go-kart while holding a Koopa shell. The mass of Luigi in the go-kart is 164 kilograms, and the mass of the shell is 11.3 kilograms. If Luigi throws the shell behind him at 31.3 meters per second, what is his velocity immediately after throwing it? See, what I'll say is initially he's at rest, and he throws the shell behind him at negative 31.3 meters per second. I said negative because it's to the left. Ow, I just punched the dot cam. Knowing their masses. And I say, what is Luigi's velocity? Any questions there so far? So, earlier I had the recoil equation. I said this equation is all recoil. And what I'm going to say is this is a recoil. It's just Luigi is the cannon and the shell is the bullet. Oh, I didn't use cannonball, I used bullet back then. That it's just Luigi is launching a shell as opposed to a cannon is launching a bullet. And I'll just say instead of bullet, I'll use shell. Instead of cannon, I'll use Luigi. The stuff on top here is always whatever is being launched. The thing on the bottom is what is doing the launching. And if I plug into that equation, the mass of the shell, velocity of the shell, the mass of Luigi, I can find the velocity of Luigi. That Luigi's velocity will be 2.16 meters per second. Questions? Any questions? This makes sense?
Yeah.
Okay. Now that's linear momentum. That's anytime two things moving in straight lines bounce off each other. That, you run into someone else, how you bounce. But that is only once again dealing with straight lines. And linear momentum is directly related to forces and Newton's third law. I'm not going to get the details there. But torque dealt with things spinning. And there's a version of momentum to deal with things spinning also, called angular momentum. Angular momentum is the momentum of anything moving in a circular path. And honestly, is a lot more interesting than linear momentum. Now, to be completely honest, to fully do angular momentum, you need calculus. But I'm going to do a low level of it and then show some of the calc-based things that it can do, because it's kind of crazy. Now, where linear momentum symbol is P, linear momentum symbol is L. And linear momentum is radius times mass times velocity. Linear momentum says that if something is spinning, it'll have at all points an Angular momentum says if something is spinning, at all points it will have an angular momentum. And it will just be how far away from the point it's spinning around it is. In this case, it would be the distance between my hands right now because it was spinning around that. How heavy is the thing spinning? And how fast is it spinning?
So is this clackers or things with the balls and the ring where you pop it up and down? I think they're
So
called
I didn't quite 100%. You broke up a little bit there, so I didn't quite understand exactly what you said.
clackers, I think, or something like that. It's it has two strings and plastic balls and a ring on top.
Oh, you're talking
Yeah.
it's like a whole bunch of balls in a line they go. So Newton's ladle.
Oh, not
That is
Newton.
actually linear momentum. Or not Newton's ladle. Newton's I'm blanking on its name too. That's actually linear momentum. I have one of them in my office at school that I use when I teach momentum in physics. Because what it is all the balls are hitting in a line and they're hitting straight on. So
Yeah,
it's
no,
so
I'm thinking of something else. I can't think of the name of it. It's literally two strings with a plastic ball on each side and
yeah, and they like bounce back and forth like this.
yep, clacker, I think.
That is yeah, I know what you mean now. That is actually also linear momentum because they bounce off each other and come back around. Angular momentum normally gets into a lot more things of objects orbiting. And I'll show you what I mean in a second. Now, like linear momentum, if the net force is 0, angular momentum is when the net torque is 0. And what it says is that if no one comes in and hits something, that anything spinning, its angular momentum stays the same. And there's a lot of practical uses of this, but I'm going to start with a less practical but interesting. Well, practical depending on what you do. If I get on a thing and start spinning with my arms out, when I pull my arms in, I decrease my radius. But if I decrease my radius, I speed up. And the reason I speed up is because angular momentum must be conserved. That if I change my radius, I have to change my velocity. This is how figure skaters do their jumps. They start with their arms out and then pull them in. Ooh, I just hit the mic. I'm sorry, that was probably loud. They start with their arms out and pull them in and speed up quickly. Same with diving, gymnastics, anything like that where someone's going to try to spin themselves. It's because if you have your arms out, your radius is bigger. When you pull it in, you decrease your radius. And if L is conserved, that'll keep the speed. See, the clacker idea, if you think what I think is because the two balls like kind of bounce back and forth, they're just hitting straight on. But this is when something's spinning and starts changing while it's spinning. And that's why, going back to me getting dizzy over here, why when I pull my arms in, I speed up. I
So like
speed.
those kids when we ran in circles or we spun our arms out, kind of.
Yep, exactly. Yep. I speed up because I'm decreasing my radius. By decreasing, or the figure skater shows even better. By decreasing my radius, I'm increasing my velocity. Okay, so example problem with this. This actually also explains kind of how comets work. If you ever hear people talking about like in sci-fi movies, they sometimes talk about like doing like a slingshot maneuver around a planet or something. It's actually the same idea.
Apollo 13.
Yep, exactly. It's the same idea. Comets, they have very elliptical orbits. And a comet, oh, I forget the words, perihelion and something something. I haven't done astronomy in a long time. But comets, when they orbit, in this case it's the sun, but also the planet when they come close. What happens is they normally have very elliptical orbits that they'll be sometimes be much closer, sometimes be much further. But it's still, if a comet is orbiting a sun or a planet, in this case a sun, it's still at all points going to follow the laws of angular momentum. And let's say that some comet, it is when it's 1.45 times 10 to the 9th meters away, it travels at 2,680 meters per second. And then it gets much closer. And when it's much closer, it's at 4.82 times 10 to the 7th meters away. We can find what its speed is at that point. See, what I'll say is I have two distances and two velocities. And my R1 being my fall distance, my R2 being my close distance, my V1 being my velocity at that fall distance, my V2 being the velocity at that close distance. Conservation of angular momentum says angular momentum should be conserved, that R times M times V should be the same everywhere. Now for this comet, its mass isn't changing. M1 equals M2. And if M1 equals M2, I can cancel it out of the equation. If I then divide both sides by R2, I can find an equation for exactly how fast the comet is moving when it gets closer to the sun by plugging in my numbers and solving. It's kind of the same idea as if I spin this and then pull it shorter and it goes real fast. It's the same thing. And that something with a very elliptical orbit will speed up like crazy when it gets close due to conservation of angular momentum. The Apollo 13 slingshot maneuver is by getting close to Apollo 13, that would be the moon. By getting close, you decrease R. If you decrease R, you increase V and you speed up and get more velocity. That's the general idea. If you change the radius, you change the velocity. Now, that is as much as you can really get of angular momentum without using a whole bunch of other things and calculus and whatnot. But I'm going to cover a tiny, tiny, tiny bit more just because there's some neat things you can do with it. I just want to show you this. One of the general ideas is that angular momentum is a vector. The direction of angular momentum is actually perpendicular to the movement, though, and it follows something called the right-hand rule, which if something is spinning, you curl your fingers in the direction of the spinning, and your thumb points in the direction of the angular momentum. So this football, if I have it spin, well, that's harder to see. This ball, if I have it spinning like this, I curl my fingers in the direction of the motion, and my thumb points the direction of angular momentum. The angular momentum points straight at you. If I'm spinning it this way, I curl my fingers, and it's pointing right at me. Not only does the magnitude of angular momentum be conserved, but the direction of angular momentum likes to be conserved. And one of the major effects of this is if I take a hula hoop and just hold it there, it's just going to fall over every time. But if I have it spinning, it'll stay upright. This is how a bicycle works or a motorcycle. If you're on a bike and you stay still, you fall over. If you're moving, you stay up. The reason a moving bicycle stays up is because it has angular momentum. Because it has angular momentum, it doesn't want to tip. Anything spinning will not want to turn. And so if you have something spinning, it'll stay straight up, even if it would normally go boop, like a bicycle. This is also why when you throw a football, you throw a spiral. If you just kind of the football, it will kind of shift in the air. But if you have it spinning, it has angular momentum. And as angular momentum, it doesn't want to change the direction of the angular momentum. So it'll stay going perfectly straight. It's also why the James Bond intro, what you're looking down is down the barrel of a gun. Rifles have what is called rifling. There's grooves in the barrel to make a bullet spin. That's what the James Bond intro is. If the bullet's spinning, it has angular momentum. It'll go straighter. And I've already talked about how this works with bicycles. To show it with another demo with this, let's say I take a wheel and I have it spinning. And I have it spinning like so. Angular momentum is going to be pointing up, and I'm sitting on a chair. I'm sitting on something that can rotate. If I have a wheel just spinning, it has angular momentum. If I turn it upside down, I change the angular momentum. But angular momentum must be conserved. So let's say I have my wheel, I set it spinning, oops, and I get on this platform. It has angular momentum. When I flip this upside down, I start moving in a circle the second I turn it upside down. Turn it back, I go back to not moving. The reason why is that angular momentum is conserved. that the initial angular momentum equals the final angular momentum. And when I flip this upside down, I go from some initial angular momentum, L1, to negative that, because I swapped its direction. And if conservation of angular momentum is true, I need to introduce, I just want this, I need to introduce a new angular momentum to make it still true. That new angular momentum I need to introduce is the angular momentum of me. That as I, I'll just cover that figure. That as I flip it, I gain angular momentum, so that the total angular momentum is still the angular momentum it was initially. Any questions though? Here's a
No.
really crazy version of this. This one is really hard to explain without calculus, but I just like to show it because it's neat. Let's say I take a wheel, the same wheel, and I just hold it by a string and let go. If I hold it by a string and let go, it's just going to fall, right? Like that's just a string that's just loosely there, not attached to anything. And so yeah, when I just let go, it pivots downwards. If I take that's the reason it goes downwards because it has torque. What's happening is gravity is going to act on the center of the wheel. That gravity is acting a distance all from the pivot point being where the string is attached, and that torque is going to cause it to spin down. But here's the
So
thing.
as a comment,
Say it again.
so a comment. When I
Yeah.
was at New York Auto Show, they do it every year. Not hasn't been a while, but
Yeah.
So one time they had a place where you sit with a chair and a wheel, and the wheel has handles, and they spun it, and you turn the wheel and you turn with the chair.
Yep, exact same thing. This is conservation of angular momentum. A very interesting thing, and this is something that I sometimes have people do in class, but can't do because I'm in person. Also, the process of turning it is very hard. Like if you just take a wheel and just go, whoop, it's nice and simple. If the wheel is spinning and you do it, it resists. You can kind of see it in the video that I don't like easily turn it over, that my arms kind of like, I kind of struggle with it a second. And I do it too fast. If I do it slow, you would be able to actually tell, but I did it quickly. That it's actually hard to flip it because it doesn't want to change the angular momentum. Okay, so with this one, if I just let this go, torque is going to cause this wheel to fall, like I showed. If I spin it though, it'll have angular momentum. And if it has angular momentum, torque affects angular momentum in weird ass ways. And what happens is that if I, there you go, just dropping it, it just falls. If I spin it, okay, and then drop it the same, instead of falling, it stays upright and just moves in a circle. That's also conservation of angular momentum. That because the angular momentum doesn't want to change, it doesn't fall downwards. Now there is some friction in the bearings. If I was playing the audio for you, you could actually hear what I that it's doing, and it's slowly falling down because friction in the bearings is slowly dropping the velocity, and as the velocity goes down, it's starting to fall. But yeah, it can actually counteract gravity because of the angular momentum. That things with angular momentum do not want to change direction, do not want to change. And since they do not want to change, we can use this to keep things exactly how we want them to be. Once again, why you throw a spiral in a football is if you have a spiral, it keeps going the way you want it and won't go crazy. Or why on a bicycle, which yes, I don't do a bicycle, I use a hula hoop just because it's easier to put on a camera, but why it will fall over every time stationary, but will stay upright when spinning until I hit something over there. Okay? Okay. I'm worried I went a little fast today because I'm done with 10 minutes left, which shouldn't have been the case. So I do apologize if I went fast. Seriously, if I'm going too fast, always feel free to let me know. But that is the end of the chapter. Homework. This is the end of chapter 3. Homework for chapter 2 is due tonight. Lab is due on Friday, and a lab dealing with forces and Newton's second law will open up on Friday. Other than that, have a good day.